Good morning, students. Um, last time we were busy dealing with the circular motions. So last time we did kinematic. So now we are going to start with dynamics.
Good morning, Miss.
Okay, so we are going to start with dynamics of circular motions. Okay, so we have said if you remember well, when it comes to Newton laws, the first law states that an object at rest remains at rest, and if an object is moving with a constant velocity, it moves in a straight line unless external forces are applied on the object. Okay, and then the Newton's second law states that in order for the object to accelerate, then there is a net force associated with the object. Okay, so here we have discussed about that when the object is moving in a circular motion, then we have that the acceleration, it moves with an acceleration which is pointing towards the center of the cycle. Okay, so from the Newton's second law, since this object is it's having the it's moving with an acceleration, then there is a force associated to that object. Okay, so then from Newton's second law, we have that force is equals to mass times the acceleration. So if we substitute that the value of the acceleration from our kinematics of the circular motions, where we have that the acceleration is given by v squared over the r. So if we substitute in there, then we have that force in the circular motions is equals to the mass times the centripetal acceleration. Okay, so that is why we have that the net force is equals to the mass times the velocity, the speed squared divided by the radius of the cycle. Okay, so and if we look up on the definition, if we consider the direction, remember we said that the force is a vector. Okay, so if we consider the direction, then we have that force equals to the mass times the acceleration. So if we look, we are saying that the direction of the acceleration is towards the center. So it means from our definition, the direction of the force and the acceleration, it's the same. Okay, so it means that the direction of the force, it's also towards the center of the cycle. So we call that force as the centripetal force. Okay, and we denote that with the FC, just to distinguish between the other forces. So as you can see on this diagram here, you can see that the force points towards the center of the earth, not the of the cycle. Okay, so that's why we have that the force equals to the mass times the acceleration of the centripetal, which is equals to that one. So the direction of that is always points, regardless at which point, as long as the object is moving in a circular motion, then the force is always directed towards the center of the cycle. Okay, so we may be wondering, what are these centripetal forces? So the centripetal forces can be any forces that we have discussed earlier. It can be a tension force, friction force. It now depends on a normal force, or it can be a gravitational force. It only depends on the object. Okay, if it is attached with a spring, if let me say you have a bob which is attached to a spring or to a string or to a rope or to a what, then the force on this object which is pointing toward the center is a tension force. Okay, so it just depends is attached to what? If it is not attached to anything and maybe just moving on that, then is it due to the gravitational force, or is it a normal force, or is it a what? We will see more later as we go with the class. Okay, so, and remember the Newton third law. The Newton third law says that to every force exists, then there is a reaction force. Okay, so but unfortunately when it comes to a circular motions, that is not always true when you have centrifugal forces. So there's always a rumor that comes up and say if an object moves in a circular motion, when an object is moving in a circular motion, and let me say that object is attached to a spring. Okay, for example, if it's attached to a spring. Okay, if this spring break here, okay, then you are saying there's rumors are saying if it's break or it does what, then that force. Okay, so remember, okay, before it, let me say before it breaks, then you are always thinking, okay, if there is a tension force, and the Newton third law, it's saying, the Newton third law is saying to every force there is a reaction force. So you may be assuming that there is a force. You may be assuming that there is a force which is in that direction, which is opposing that force towards the center. Okay, so you may be assuming, no, then this means there should be a force which is opposing that force. So if there is another force, then it means this object won't move in this direction. Like it won't move in a circular motions. Because of that force which is opposing it, it is movement. So this is not always, now this is not true when it comes to a circular motions. In order for the object to move in the circular motions, then the only force which exists is the centrifugal forces. So, okay, so there is okay, so the network is failing us. So we have that what were we saying? We were busy with this. Okay, so if an object is moving up on the circular motions, okay, then we say that there is a force always pointing towards the center of the circle. Okay, then over here you are saying Newton third law, maybe like for the every force there is a reaction force. So if this is true, then this object won't move in the circular motion. So this does not happen. So there is no centrifugal forces for the object to move in a circular motion. So this force does not exist. It's only the centripetal force that exists. Okay, now let's see what happens if the object was moving in a circular motion. Okay, so this was the object which is attached. Okay, so this is the object attached to a spring. What happens if this spring just break? Okay, so if this spring break, then remember we said that the velocity of an object is always tangent to the circle. Okay, so if that spring break, then your object will not move on that direction. Okay, so it will still it will continue to move in the straight line, because remember we say that the velocity is tangent to the circle. Okay, so if it was at that point and then the spring break, the velocity was directed towards that when the spring was connected, then this object will continue to move up on a straight line like that going up. Okay, so it's no more going to move in a circular motion because of the effect that there is no force which is holding it to keep it moved up on the centripetal force. So it will continue to move in a straight line, but it will not change its direction. Okay, so, and this is what is happening here. So if the spring breaks, so the direction of the motion, okay, of the ball when it breaks, so if it was directed towards that, it continue to move up in that same direction over with a straight line. Okay, so we have seen that there's a centripetal forces. So this is to every object moving up here. So it's like you can see here, if this is a car moving up in a curve, then you can see there is a frictional force on the tires. This is with a rope, then there is a tension force. This is due to the earth gravitational forces, then this is due to the the gravity force. Okay, so let's see if an object moves up in a circular motion. Okay, then we want to see what which forces are acting on the object, okay, as it moves on the circular motions. Let's say if you have an object at the bottom of a circle, okay, then you have that as the object is at the bottom of the circle, then you can see that there's a normal force which is perpendicular to the surface. You have a weight. Okay, remember every object is associated with a weight, and the acceleration on this, because the object is like it's moving up on that, and it says that your acceleration is always towards the center of your circle. So we have an acceleration pointing upwards in that direction. Okay, so if we use the Newton's second law on all the vertical forces that are acting, okay, then we have that the forces, if we sum up, if we take the upwards to be our positive, then we have that the normal force minus the weight is equal to the mass times the acceleration. Okay, so remember our acceleration is equal, because this is due to the centripetal acceleration, is equal to the velocity squared divided by the radius of the circle. So if we put it in there, we solve for our normal force, then you will see that we have our normal force is equal to the mass times the acceleration plus the weight. So when you're at the bottom, so when you are at the bottom of the circle, then so if you are here, then you feel more heavier. As you can see on the equation, it's saying the normal force is equal to the weight plus, so you are adding something to your weight, so you will feel more heavier when you are at the bottom of the circle. Okay, let's see when you are at the top of the circle. Okay, remember you are still inside the circle, you're just moving up there. So when you are at the top of the circle, then remember our acceleration is always towards the center. Then your normal force, remember it's always is perpendicular to the surface. Your normal force now it's pointing downwards. Then you also have a weight which is always due to the gravitational acceleration. Okay, from our previous example, we have that the up, it's our normal our positive when it points upward. So we have that the weight, if you use the Newton's second law again and we sum up all the forces, then we have that the normal force is equals to the weight minus the value of a mass times the acceleration. So when you are at the bottom, you feel lighter than when you are at the top of the at the bottom of the circle. So when you're at the top, you feel more lighter than your weight. Okay, so this is just almost like what we were doing at friction forces when we were looking at the apparent weights. Okay, so this is what you will feel when you are at the top of the circle. Okay, so let's say if you are outside the surface, Okay, so if you are outside the surface, this is on top. Okay, there you were inside. Now let's see if you are outside. If you are outside at the top, then you apply the same, the acceleration goes there. Then you have that the normal minus the weight, it's equals to, okay, here you are up. That's why you can see that your normal force is now directed towards its upward. Okay, so we have that the normal force, to do that you add up, then you have that the normal force is equal to the weight minus the mass times the acceleration. Okay, so here remember, don't confuse this one with the previous one that you were doing. Here you are on top of the surface, here you are outside the surface, while the other one you were inside this, like this, the surface. Okay, so here when you are on top, you will feel lighter, okay, than your weight. So that's why you have that the weight minus that is equal to that. But if you look up on this one, this is all, it's almost the same. It's just the same as what you feel when you are inside. So it's just the same here. Okay, so if the acceleration, if you have the acceleration is due to the gravitational acceleration, then if you add normal force is equal to the weight minus, if this is the gravitational acceleration, simply here you're also getting the acceleration, then your weight weightless, so there's no weight on you. Okay, let's see what happened to the horizontal. There you were looking up on the vertical motions. What about when you are on the horizontal motions? Okay, so this one we'll look at with bent or unbent curves. Okay, when the curve goes around a curve, there must be a net force, okay, as we said, towards the center of the, which, okay, in order for the object to move in an arc. Okay, so if that force is applied, it's a frictional force. Okay, then here you will see that if you have a car, okay, which is going up in the circular motions, okay, then here you see that you have, okay, if you are inside the car, then this is the force on the passenger, like you have, so that means the tendency for the passenger to go straight. Remember we were saying that the force, okay, remember here we were saying that if an object is moving up in a circular motions, okay, so if this is a car and you are inside that car, the way you feel more that you really don't feel that force. It's like you are just moving with like in the straight line, while the car has a force which, as it moves in the circle motion, so there is a force which is directed towards the center. Okay, so as you are there, you're more likely not to feel the, as you can see here, the tendency for the passengers goes straight. Okay, so as you are inside there, you are feeling you are going straight, but the car is moving actually in the circular motions with a force directed towards the center. Okay, so if the frictional force is insufficient, okay, so if there is no enough force, remember that you are saying the force on the tire is on the road is due to the frictional force, it's insufficient, then the car will tend to move more nearly in the straight line as the skidding marks shows there. So as you can see up here, okay, so if the force, you can see here, you can see that the car needs to go up on the straight line, I mean on the curve. Okay, but if the forces on the tire is not enough, or on the road is not enough, then the tendency for it, as you can see here, it's more likely to go up on the straight line and go turn a bit far. Instead of it to turn closer here, it turns far. This is just due to the frictional force, which is not enough or not sufficient to that. So as long as the car do not slip, that it doesn't go out, then the friction force is static. Okay, if the tire do start to slip, then the friction force, which is bad in two ways. The kinetic friction is smaller. Remember this. So it's skidding is like it starts to move out in how will I say now, moves up in more likely like it's going up in the straight line. Okay, so it's like it's going out of the road. It's doing that instead of it to follow the road, it now starts to move out of the road. Okay, so the static frictional force can point toward the center of the cycle by the kinetic frictional force. Okay, so opposes the direction of the motions, making it very difficult to regain control of the car and continue around the curve. Okay, so remember we are saying that, okay, so for the car to move up, the friction force must the kinetic friction force must be smaller than the applied force in order for the force to for the car to move. Okay, so if you have that the static force can point towards the center, if you have the static force it's pointing towards the center, but the kinetic force opposite the direction, so then it make it difficult for the car to move, and the car will just move out of the road because you cannot gain control out of that car. Okay, so if this is unbanked curves, okay, so then here if you're on the top view, and remember we are looking on the horizontal forces, né? So if you are at this point, so we are looking up on that forces that goes, we are looking up on that forces that says if this is a car moves up on the straight line, what happens when the car is there? So we are looking, we have done with the upward and downward. This is the, I mean with the, when the vertical motions, the up and down. So now we are looking at the horizontal motions. Okay, so remember, okay, if the car is at that point, okay, so if the car is at that point, what happens to the forces, and what are the forces acting on that object? So the remember that your object continues to move. The velocity at that point is still directed in that direction. Remember, you're saying it's always tangent to the surface, and there is an acceleration pointing up on that. Remember, it's pointing up on that direction, which is towards the center of the cycle. Okay, so the normal force of this, okay, when you're at the top view, then you have a normal force, which is directed in that direction, and then we have a force of gravitational force, which is always on that side, and so forth. So if we sum up here, okay, while on this the horizontal surface, remember if we say this is a car moving up on that direction, you only have the friction force. Then we have, okay, let's forget about the normal force, let's just leave it up for now. Then we have that on the horizontal surface, we only have the frictional force, which is opposing up on that direction, which is equals to the mass times the acceleration. Okay, so remember we are saying that the frictional force is equals to the coefficient times what? Times the normal force. Okay, so if you look up on this equation, the normal force acting on this is equal to the mass times the gravitational acceleration. So if we substitute up there, and then we have the static friction, so if you substitute up there, then this is what we have. So then we have that the normal force, I mean the friction, so if you put the mass cancels out, then we have that the kinetic coefficient times the gravitational acceleration is equals to v squared times the r. So if you have to find the velocity, then if we know what is the coefficient, what is we know the gravitational acceleration, we know what is the radius of it, then we can make use of it to calculate what is the accelerate, and then the velocity it moves with as it goes there. Okay, so the bent curves. Okay, so here it helps Okay, so the bent scale can help the car from skidding, like moving out in a straight line. So in fact, for every bent curve, there is one speed where the entire centripetal force is supplied by the horizontal components. Okay, so if we look up on this, okay, so if we consider, say, okay, if you look up on the top view and we're saying, okay, if it is associated with an angle, okay, so then we have that the acceleration on this object on the horizontal vertical, it's now looks like this. This is your object and is at the incline. Okay, so it's like okay, bent curve must be just like the incline curves. Okay, so if you have an object associated, if it is at the what at mixing up an angle with the horizontal. Okay, so then remember, if we go back to the incline, then if we draw up, okay, our axis, more actually the incline. So in fact, when the bend curves, there is one speed. Okay, so if we have this, okay, this is just what we have. Okay, so if we have up something like this, okay, so if this is your object moving up on that, okay, remember now on the incline, our object was like this with a surface. If this is in a surface, okay, we can say this is my x-axis and this is my y-axis. Now if we look up on this car, it's straight on that direction, then we say that okay, our x, if this is how your object is moving, at that point is facing on this side. Okay, so you'll see that the so if you point, you can see that your x, by choosing your x-axis, so your x-axis, say it's pointing up on that direction and your y-axis is upward. Okay, then by drawing our free body diagram, the meeting will end in 10 minutes. Okay, so but please log in again. Okay, so we know that the direction of that acceleration is towards the center. So if we create that, then we have our x-axis. So we have that our y-axis points up and our thing points down. So then where is our x-axis? Is this one, which means it's always points. So our x-axis points towards the center of the what, of the circle, not on this side, because that is not where our or else if we choose this direction, then we are saying that this is not toward the center but it's on the component. So it's like we have x-axis pointing, I mean the acceleration in x and y, but your acceleration must point towards the center of your circle. Okay, so with our acceleration pointing towards the center of the circle, we can say this is our x-axis and the upward is our y-axis. So remember, we have a normal force acting on that object. So what is a normal force? You can see, as we said, it's always perpendicular to the surface. So this is the direction of our normal force. Okay, so having that, we know our y-axis. Okay, so you can see that our normal force at this point is acting in what? Is acting in angles. Okay, so it's acting in both x and y. Our normal force here is no more pointing on the y-axis as what you were doing on the incline. Okay, so remember, okay, this is our incline that we have making up with an angle theta. Okay, so and this object moves up on the circle, just to make it easy for you to understand nicely. Okay, so it moves up in a circle. So when the object is up at this point, where remember that the acceleration is always points where? Towards the center of your towards the center of your circle. Okay, so which means that if this is our acceleration and this is our object, okay, that means our x-axis, so by choosing our x-axis, this is your x-axis and this is the upward, your y-axis. Okay, so as the object is at this point, where is the direction of the normal force? The normal force, remember, is always saying is perpendicular to the surface. So the normal force is pointing up on the direction, not on the, because now if we consider the incline was saying, in the incline we were saying this is the upward is our normal force, like this one. Okay, we can say this is our normal force with our y-axis being on this direction and our x-axis being on that. Okay, you can say our x-axis being on that direction, depends on where we are forcing. My drawing. Okay, so if this is the incline, on the incline we were saying if this is the object, then my x-axis points up on that direction and my y-axis points up on that direction. Okay, so if we consider, if you look up on this one, this is my x-axis and this is my y-axis. So you can see that here your perpendicular is going up on that, this is your normal force in that side, and my weight in that direction, which is now the one which is making up an angle. Okay, so okay, this is the weight, this is on the incline. Okay, so now if you consider up an incline on a cycle, if this is an incline on a cycle, if this is an object and this is how your cycle looks, okay, remember it's saying it goes in a cycle, so your acceleration should always point towards the center of your cycle. So this is the direction of your acceleration, so choose a different x-axis from this one. Then we were saying on the incline, we were saying the down one, this one is our x-axis. Okay, so now here our x-axis is the one which is pointing where the direction of the acceleration. Okay, and our y-axis up on that direction. So if this is my object, then we have that my normal force is actually towards this. Okay, then it means my normal force is acting up on an angle. Okay, so it means I have a normal force. Can we draw maybe somewhere here? So you have a normal force which is operating in y components, and you have a normal force. Okay, a normal force, let's just put it here, operating in or existence in the x direction. Okay, so if it means that your resultant normal force is going to be equals to the normal force in the x direction plus the normal force in the y direction. So if you just consider the magnitude, then this is equals to the normal force in x squared plus the normal force in y squared. Okay, so keep in mind that the x your axis on the incline or on the bent curves is different from when you just have the incline, so the axis differs. Okay, so very, very important to keep in mind. So with that, that's why we have up these equations here. Okay, so you can see that your normal force in y, it's given, if you consider in the angle, this is our opposite, this is our adjacent. So the normal force in y is equal to the normal times the cosine theta, while in x is equal to the normal force times the sine of an angle. Okay, so as you can see here, we have that a normal force, as you can see up, come on, as you can see up here, okay, that the normal force times the sine theta. Remember from the up one there, we had where there is no unbent, like just moving up on this on the surface, straight line surface. So then we have that the normal force is equals to mass times the acceleration in the x direction, I mean. So we have that. So what plays a role here? The one that is playing, it's like the centripetal force, which is acting towards the center. It's now this one. This is the one which plays a most role for this object to move in the circular motion. So you will see that the normal, if we sum up, because this is the force which is acting towards the center. The force which is acting towards the center here is the normal force times the sine of an angle, which is equal to the mass times the acceleration. And this is the most important force that plays a role for the object to move in the circular motion. That is only true if you have an object moving in the on the curved, okay, on the bent or on the bent curve, okay, so like it's making up an angle. Okay, so if you look up on this example, so we have that a 40 kilogram attached, okay, and it's rotated in a circular motion with that radius on a frictionless, so that there's no friction on that surface. So if the cord break, okay, if the cord will break when the tension exceeds 60, okay, so if that cord, okay, remember you're saying it's attached to a cord, if it breaks when the tension is equals to a 60 Newton. Then what is the maximum speed the ball can have? Okay, so remember, okay, let's look up onto this one. Okay, so this is ball attached to a spring. This is where your ball is attached to a spring. Remember, we are always saying the force, it's always towards the center, and this is your tension force. Okay, so if the object was moving, and then we are given that after that, when the tension is equals to 60 Newton, okay, and our acceleration is towards the center. Okay, so if this is equals to 60 Newtons, then that one will break. Then what is the velocity? Okay, what is the velocity will the object have? So from the Newton second law,